Welcome GeoTrig. This is section 5.3, bisectors in triangles. The essential question is, why are bisectors in triangles useful? Let's begin. So a few vocab words. If we have a bunch of lines right here, and they're all crossing at this one point, we have vocab for that. So we have this word called concurrent. Concurrent are when three or more lines intersect at one point. So we say all the lines are congruent. So the lines are concurrent. So when three or more lines intersect, those lines are concurrent. That point of concurrency is the point where they all intersect. So this point right here, that is my point of concurrency. Point of C. So that's what's going on. So, all right. So what do we use that for? Well, we have a concurrency of perpendicular bisectors theorem. What does that mean? So we got this triangle here. And if the perpendicular bisectors of the sides of a triangle are concurrent at a point that's equidistant from all vertices. So perpendicular bisectors, that's what we talked about last section. So we got all three right here, and they are concurrent at one point that is equidistant from all the vertices. So all three red lines right here form a point P, and this point, the blue dash marks, basically saying the PA, PC, and PB are all the same length. So that's kind of cool. We have this other idea. Circumcenter of the triangle is the point of concurrency for the perpendicular bisector. So basically this point, we can draw a circle around the triangle, that actually a better circle than I did. A circle that hits all three of the vertices, and this is called a circumscribed triangle or the triangle has a circle that's going around it. And that point in the center that's concurrent, that's the center of the circle. And it's like these are all a bunch of radiuses of the same length, or radii. So the circumcenter doesn't have to be in the middle of the triangle. It can be in the inside, it can be on the side, or it can be on the outside. So we got three cases. In an acute triangle, it's going to be in the center. If you have a right triangle, it's going to be on the hypotenuse. And then if you have an obtuse triangle, that point is going to be outside of the triangle. So why is this useful? Well, one way is if you're trying to plan like a... Alright, so why do we use this? Well, let's take this example, this town. So town wants to put a new fire station, and they want to put it equidistant from both elementary, middle, and high school. Well, where do you want to locate this? And so this is the application for this, because you can't just say, well, I'll put it in the middle. And maybe in this case, because they're all kind of close in this picture, you can. But what if the middle school is out really far? I mean, you want to use math to figure out where I can put the fire station so I have the same response time to every school. So let's draw a triangle between all 3 points right here. If we draw this triangle, and then we can look for perpendicular bisectors to each of these. So what's the perpendicular bisector going to be? It's basically kind of got to eyeball this in this picture. Well, you got a perpendicular bisector from this point, probably going out like this. You have a perpendicular bisector from this point, going out like this. And in this case, well, this kind of formed a right angle right here. So we got a little bit lucky, and that the firehouse would be right here. This is where all 3 points intersect. So that's where you'd want to put the firehouse. Maybe not the best example, but we'll do more in class. All right. Concurrency of angle bisectors theorem. So this is the other thing, the angle bisectors. Okay, we talked about the perpendicular bisectors, the midpoints. Angle bisectors is different. So the bisectors of every angle in a triangle, any triangle, are concurrent at a point that's equidistant from the sides. So we draw the bisectors for A, B, and C here. They're going to have a congruent point right here at P. And then what we can say is the length from P to X, P to Y, and P to Z, or just the length from that point to each of the sides, is going to be equal. And this is a neat property here. So this point here, it's always going to be in the middle of a triangle when we do this kind of stuff. But basically, we found a point that equidistant to every side. Instead of the last one, we had a circumscribed triangle. This one, this point right here forms the incenter of the triangle. This is the point of concurrency of the angle bisectors. So basically, we have a inscribed triangle here. So there's going to be a circle inside the triangle, and this point P is basically going to be the radius. P to one of those sides is going to be the radius of the circle. So inscribed triangle for this. All right. So what's the use of the incenter here? Why would we use this kind of stuff? And what's neat about this is we found a point that is that's the same distance from every side of the triangle. And a lot of this is if we're trying to design a architecture or design a layout of some kind of plot of land. We want to put some houses. We want to put some buildings. Maybe we have a bunch. This is a triangle This is a triangle shopping center, and these are a bunch of parking lots. And we want to figure out where to put the building so it's the center of everything. That's where this kind of math comes into place. Sometimes I know you could probably eyeball it and say, "Oh yeah, the center's probably there," but it's nice when you have different types of triangles to have some kind of formula to say that yes, this is the point right here where it's going to be equidistant to every side. But we'll do some more in class. Anyways, do some examples. Pause the video. Okay, so we say GE equals 2x minus 7 and GF equals x plus 4. What is GD? So this side right here is 2x plus 7, 2x minus 7, and this side here is x plus 4. How do we do this? Well, okay, the neat thing here is this looks like these are all right angles here, and judging by the arc marks on each of these are all angle bisectors. So G is going to be the concurrent point. So point G equals concurrent. So what I know about these concurrent points is that each of these lengths here is the same length. So I can create an equation, 2x minus 7 has to equal x plus 4, and solve for x. So I'm going to subtract x on both sides, and I'm going to add 7, and I get x equals 11. So if x equals 11, what's GD going to be? It's going to be the length of any one of these other ones. So I'll just plug in 11 and find out. So since GF is going to equal 11 plus 4, which is going to be 15, then GD also has to equal 15. Next one. Pause the video. All right, what are the coordinates of the circumcenter of the triangle? So circumcenter, that goes back to that first theorem here. Circumcenter of the triangle. So that's that point in the center of, or that's the point of concurrency of the perpendicular bisectors. So basically, let's draw the perpendicular bisectors and find the point. Okay, so perpendicular bisectors is a perpendicular line that's from the midpoint. So I'm going to start on this side. I know the length of this side is 6 because it goes from 0 to 6. So the midpoint is going to be right here. Now, if I draw a line perpendicular to this, guess what? It's pretty easy. This is left and right. So the line perpendicular is going to be straight up and down. So it's going to go just like that. Now let's do the right side. This goes from 1 to 4. So the middle, that's going to be a length of 3. Middle of that's going to be 1.5. So the point's going to be about right here. And since this is straight up and down, a line perpendicular is going to be going left and right. So I can draw a line going like this. Now, the neat thing, I know triangles have 3 sides, so you think we'd have 3 of these perpendicular bisectors. But the neat thing when we're just trying to find a point, to find any point, we just need 2 lines. Because 2 lines where they intersect is the point. If we had to draw a third line, even if this wasn't a right triangle, all we'd ever need is 2 of the points. Because they'll always cross at one point. We have a third point, it'll still cross at the same spot. So the coordinates of the circumcenter are right there. Well, what's the coordinates right here? I think my x value is clearly 3. And this went up to, what's this? It's halfway through, so that's going to be 2.5, so 2.5. So that's my coordinates of the circumcenter of the triangle. That's it.